In a real gravitational field, of course, like in the Earth, where you have different strengths depending on the height, so the top floor of the building obviously has slightly less gravitational acceleration than the bottom floor, and different wings of the building have a slightly different direction towards the center of the Earth. If you take two particles and you let them go, then they both fall straight down, but they're aiming towards the center of the Earth. So I'm going to exaggerate the difference, but one is kind of aimed like this, and the other one is aimed like that. Obviously, I'm exaggerating greatly the angle between them, but clearly they have a different direction of acceleration. Also, if I hold one above the other and I let them go, this one being closer to the Earth than this one will have a greater acceleration. So this one accelerates down more than this one does. So between the two, there will be a relative acceleration. This one is accelerating more than this one. Now, the word for these accelerations, these are relative accelerations, we call them tidal acceleration. If you see particles accelerating relative to each other, I mean, it's clearly obvious that they are not inertial. Now, you can say one of them is inertial, the other one is accelerated, but they're two identical particles in the identical situation. There's no way to distinguish one from the other, and you can't say that one is accelerating the other. Obviously, if one is accelerated, it's because of gravity, and then so is the other. So this relative acceleration is a clear giveaway to the non-inertiality of these particles. So again, there we are. You know, finished, model is over. Right? Can anybody suggest a way around that? We can maybe come up with a way around this and say that in the same way that gravitational accelerations disappeared in free fall, right? If you're free falling alongside something else that is in free fall, there's no gravitational acceleration, they move inertially. Maybe this also disappears in free fall. Right? If this phenomena disappears in free fall, then it's not a real phenomenon. It's just something you observe from a non-inertial frame, this accelerated frame, the Earth stationary frame. So what do you think? Does it disappear in free fall? So if you think about it, you'll see, and if you're falling alongside them, then the average, so to speak, is wiped out. The average acceleration between the two, if you're in the middle, will be wiped out. What you will experience, you will see this one accelerating away from you with the difference, and accelerating away from you in this direction with the difference. The amount that this is more than you, that's the amount that it will accelerate downwards. And the amount that this is less than you, lesser acceleration, you will see it accelerating upwards, right? So you're accelerating with the same acceleration as their average, and therefore all you notice is this one going up with a less, and this one going down with a more. Okay, as you're falling, you see this kind of motion. So what you see is that. And what you see when these two particles are accelerating this way, and you're going straight down, what you see is this one and this one, both of them accelerating towards you, okay? Because they're accelerating like this, right? But the downwards acceleration is canceled out by your free falling alongside them. All you see is this component. Now the question is this component a relative speed or an acceleration? You can see, and you can do the math, that if you're accelerated along this direction, you're going to accelerate in this direction and that direction. So you're going to have a relative acceleration between the two. So what you notice is, if you put a bunch of particles, these will separate, and these will converge. All right? Now, in Newtonian gravity, you can do the calculation, it's all over the web. You can see that if you took a sphere of particles, separate particles that are just put together in the shape of a sphere, they're not glued together, as it falls, it will turn into more like an oval, like a football, like an ellipsoid. And it turns out that the volume remains the same. That's a beautiful result, and it has to do with the fact that its divergence, div A is equal to rho. We try to get around this objection to the model by saying that maybe in free fall the phenomena disappears, and we can see no, the phenomena does not disappear in free fall. There is incontrovertibly a relative acceleration between the particles this way and that way, even in free fall. So that would seem to make this model completely inconsistent. And all these are identical systems and identical states and so on. There's not that one of them happens to be accelerating the other. There's a relative acceleration between them. So obviously they're all accelerated and they're not inertial. And so again, there goes the model. But of course Einstein said, no, I'm not giving up this model. Now, can you think of just some audacious way around it? Einstein didn't accept that. Einstein went ahead, he said, no, this is true. I know a way around that. I'm not going to refute any of the statements, I'm just going to blaze forward. Just say, well, it's very nice that there's a relative acceleration, so that is the phenomena of gravity. Gravity is the relative acceleration of inertial particles. You have neighboring inertial particles. They are inertial. Each one is inertial. But there's a relative acceleration between them. Now it sounds absurd. You say, well, that's impossible. So Einstein says, no, that's the fact. You cannot distinguish any of the individual particle state from an inertial state. And therefore, both of these particles are indeed inertial. And yes, there is a relative acceleration between them. And so that, and not gravitational acceleration, is the phenomenon. What we thought was the phenomenon of gravitational acceleration, right? Changing the trajectories, that is not real because that disappears in a free fall frame. Those particles are inertial. What is the phenomenon of gravitation is the relative acceleration of inertial particles. And that's just a fact. That's a fact about nature.
Einstein modeled Newtonian gravity as a relative acceleration of neighboring inertial particles, which we'll abbreviate as rag. This is something of a conundrum. It's very nice for Einstein to claim that in the presence of matter there's relative acceleration rag, but how can that be? Why is it okay for Einstein to simply assert what we would otherwise assume is impossible, that inertial particles can have relative acceleration between them?
Gravity is not about particles accelerating, as one thinks about it in ordinary physics and Newtonian physics. In fact, what gravity is about is inertia. Inertial particles, when encountering a region where there is matter, and of course when we say encountering a region, obviously the effect of gravity goes off. In Newtonian physics, it's 1 over r squared, so it goes off forever, it just decreases. So it's really everywhere, but we'll say someplace where you wouldn't notice it, like distant intergalactic space. You can't even see any galaxies anywhere. As far as you know, you don't measure any gravitational effects, right? You have an inertial particle, you're satisfied that it's inertial, and it eventually you're riding along there, you're in this rocket with the rocket off, so you're inertial. And eventually, one day you wake up and you see your measurement instruments indicate that there's a galaxy up ahead. So you know something was moving. You were moving, they were moving, whatever. You got closer to each other. And now there will be gravitational effects. Or maybe the gravitational effects can come before you notice the distant galaxy in your instruments. It doesn't matter. But what will happen? You and everything inside your spacecraft will not change from being inertial. you're all still inertial. Just they experience a relative acceleration. What matter does, it has an effect on the medium, such that although inertial particles remain inertial, they experience a relative acceleration. So if you remember, we had, say, planet Earth over here. We had particles, if they dropping straight down to the Earth, of course, straight down to the Earth means straight down towards the center of the Earth. So they accelerate this way, exaggerating the angle, and there will therefore, in free fall, will be a relative acceleration between this way. If you drop them like this towards the Earth, obviously this one being closer to the Earth has a greater acceleration than this one, so there will be a relative acceleration between them, and that will be visible even in a free fall frame. So it's a real phenomenon, and the real phenomenon of gravity is the relative acceleration of inertial particles, where, again, since it's inertial particles, there is no way to distinguish an inertial particle in a gravitational field from one that's not in a gravitational field. It is inertial. The way to distinguish things is when you have neighboring inertial particles and you notice the relative acceleration. We have this beautiful model, which is a very radical understanding of gravity, and we would want to find some kind of mathematical basis for it. The next lecture, not sure when it will be, will take everything that we discussed and model it mathematically, and we'll see why we're led to the notion of the existence of a space-time, why it has a geometry, what the geometry has to do with all this, and specifically what space-time curvature has to do with all this. Thank you for your attention.